Hello everyone. Well, we are on our final module, not our final module, but our final module where we're going to be introducing new materials. And this week we're going to talk about clustering. This is actually an easier topic than some of the other topics that we've talked about because clustering is an unsupervised process. Unsupervised meaning that we don't have to go back and look at old data sets. We don't have to pull in an old data file and divide it into a train.df and a valid.df and run processes on train.df in order to identify the records that we want, etc., etc. What we're really doing with clustering is we're just loading in a file and doing all of our work on that file. So there's no training piece, there's no supervised piece, this being an unsupervised process. We're going to use a utilities file, utilities.csv file that the textbook has given us, and we're going to run two types of clusters on it. Now, if you've looked at the videos that I've shown you, there are videos that talk about hierarchical clusters like agglomerative and divisive, and then there are clusters, different types of clusters, like k-means and k-medians. And they basically do the same thing. What really is different about clustering is your distance algorithm. Your distance algorithm is, well, let me step back for a second. Clustering is based on, let me step back further. When we cluster, we are looking at arranging records, data points in our data set in order of how close they are to each other. In other words, in order of how similar they are to each other. And so we gauge that similarity using distance metrics. And distance metrics will basically say how close is a record to every other record. Euclidean distance is the easiest and most common. What we're basically doing is, for example, if we're basing our cluster on two variables, variable A and variable B, we will take variable A for the first record and subtract out variable B from the second record. Then we will take the square of that value. We'll do the same for variable B. We take variable B from the first record, subtract out variable B from the second record, take the square of that. We combine those two and take the square root. And that gives us a single numerical value of the distance. It's a cumulative distance between record A and record B. And so where that's small, we presume that the values in the variables are very similar. Of course they would be because they're derived that way. Where that's very large, we presume that the values in the variables are very large and they would not be in the same cluster. The small distances, similar records, same clusters. Large distances, non-similar records, different clusters. And we'll see that when we run our clusters. What I have done is I put together a clustering script. It's largely based on the script that's in the textbook in chapter 15. And I'm going to run through it real quick. It's very simple. Very simple in the sense that there's really not much to clustering, partly because it's unsupervised, and partly because it's just so easy in R. Okay? So you've got this cluster script that is actually sitting in your Canvas shell. It's in Module 15 under Resources. So you can go ahead and download this script. You can also download the utilities.csv file. That's also sitting up there in Resources. I put a lot of comments in so that we can actually work through these. And so let's go through this. We'll go blast through the comments. Okay. First thing we're going to do is we're going to load our file. File's loaded. Okay. The next thing we're going to do is we're going to actually use the row names. We can identify row names. It's a different variable, and we can set row names, and that's going to be helpful for us when we want to actually use those names in the clusters themselves. So we're going to take one of the fields, and we're going to move it into row names, and that's just basically going to be the name of the cluster. Or the name of each row, the name of the utility. And so we'll drop that into row names, and then we'll remove it from our data frame, from its original spot so that we don't have, it's not duplicated, right? It would be silly to have it duplicated. But having it in row names allows us to use it as a label in our clusters. So we'll go ahead and do that process. Okay, now we're all set up with the right kind of row names. All right, the next thing we're going to do, remember I talked about Euclidean distance. Euclidean distance is the way that we calculate how far one data point is from all other data points. And the best way to do that is to really just look at, kind of just run a comparison, cross comparison of every data point to every data point. Then we have got our values, and once we have our values, we can start thinking about, okay, which ones are really small values as far as distance between A and B, or A and C, A and D, whatever, and which ones are very large distances. And we can start using that information to combine data points into clusters. So the first thing we would do is we would actually set up to run the calculation of the Euclidean distance, and this is the way that we compare every data point to every other data point. I've dropped those results into a variable called D, and then I'll just print out D. And D is actually really long because we're looking at the distance of every data point against every other data point. And we can start seeing that it builds this data frame that shows us how close is Boston to Arizona, how close is Boston to, we go over to Boston here actually, how close is Boston to Central, to Commonwealth, all these other ones. Where we see that the values are low, that might mean that San Diego and Boston might cluster together. Where we see that the values are very high, it would mean that Boston and Arizona, they're distant, they're far apart from each other, so they're probably not going to cluster together because in reality, in real world sense, the records probably aren't acting in the same way. Okay, so that's how we calculate Euclidean distance and how we might use it. But you know what? There's one step that we left out, and that is, remember when we did KNN classifier, we had to normalize our data points, because if we didn't normalize our data points, those values that have large ranges would take too much weight and it would throw off our calculations. Well, we have to do the same thing in clustering. So we're going to go through and actually normalize the data points. So what we're going to do is we're going to set a data frame utilities.df.norm, and we're going to sapply is basically says apply to every value. So sapply is kind of a global apply in utilities.df, and we're going to say apply the scale function. Scale function, if you remember from statistics, is basically just converting to z-score. You basically take every value, you subtract the mean, and you divide by the standard deviation. And so it gives you a value of anywhere from -3 to +3 typically. And so that's what we're doing, is we're giving those values a z-score. So we'll go ahead and run that. All right, and then we're going to change that value. We're going to actually put the row names in, just like we did before. We want to use the same row names that we have in our data frame so that we can identify what those values are. And we're going to now calculate the Euclidean distance on the normalized values. So now we're going to calculate Euclidean distance in a way that makes better sense. And we get the same kind of thing, right? We get the same kind of values. And if we go to the very start of it, we'll see that now, I went too far up, sorry, let's go back down. Now, the distance between Boston and Arizona is 2.0. Remember I said it's going to be on a scale of -3 to 3. This is still pretty high, though, because it's 2. It's like 2 standard deviations away, where others are like down here in the zeros, in the ones, right? And so we now have a normalized distance of every utility from every other utility. And now we can build our cluster on this because it's going to give us a much more accurate result. So the first kind of cluster that we're actually going to build is going to be our hierarchical agglomerative cluster. Hierarchical, you see why it's called hierarchical when you see it. It's just basically a stack of different values that are on a hierarchy. But the way that the agglomerative cluster works is when it starts out, if we have, say, 35 different utilities, you're going to have 35 different clusters. And then you're going to work your way backwards. You're going to find the 2 that have the least distance, and you're going to join them. And you're going to keep going through that. You'll find the next one, whether it be the cluster that you just created with 2 nodes, or all of the other clusters that have a single node. You find the next one with the smallest distance, and you'll merge that one in. And you'll keep going over and over again until you've accounted for all 35 of the nodes and built that into your hierarchical structure. So that's what we do with agglomerative, is we take all of the nodes, start out being their own cluster, and then we just merge them, starting with the one that has the smallest normalized Euclidean distance, and we work our way back. Let's go through that first process. All right. So now we're going to go ahead and build these, and there's a little bit in the book that talks about similarity measures and distance measures, and we're going to use 2 types. We're going to use single, and we're going to use average. I will let you look in the book. The book talks about these very well. I'm going to skip them for now, but just know that there are 2 different ways of being able to determine distance or similarity between the data points. So the first one we're going to do is we're going to set HC1, which is just a variable, is going to be set to hierarchical cluster. That's a function in R. And we're going to use the D norm. That's the data set that we created up here. And the method we're going to use is single. So we'll go ahead and do that. And then when we're done with that, we'll plot it out. We'll plot HC1. The hang equals -1 determines where our labels go. And the ANN is annotation equals false. It says that we're not going to put any annotation on the plot. We're just going to leave that off. So we'll go ahead and run those. And there's our plot. There's our first plot. Now it's kind of small, but if we expanded it out, we'd be able to see how our utilities cluster. And what you're able to see on this also is you're able to see a little bit of how things are similar. So New York, Nevada, and San Diego are kind of similar, but when you get down here, you see it Hawaii and New England and United, they are all very similar, and they're very similar on the values we selected to run the cluster. Okay, let's go to the next one. The next one is just a different cluster. HC2 is being set to the value of the hierarchical cluster using the averaging method. We can plot that, and it gives us a different cluster. And the only difference is the way we determine the similarity and the difference. Now, if you start to look at this, the very top branch has this cluster set against all of the rest of the utilities. So Nevada, Idaho, and Puget are clustering together. Everything else is breaking out separately. So if we take one branch down, we look down, we see that New York is kind of, the cheese stands alone with New York. It's kind of on its own there. So then we look down one level, and we've got two splits here. We've got one cluster here that has San Diego, Pacific, Hawaii, New England, and United. That's all one cluster that's clustering together. And then you've got Madison, Northern, Commonwealth, Wisconsin, all Boston and Virginia, all on this sort of subcluster. And you've got a sixth one over here that is Central, Kentucky, Florida, Oklahoma, Texas, Arizona, and Southern. The positioning of the dendrogram, we call this a dendrogram, and the positioning of the dendrogram is very important because the smaller the branches, the more similar the nodes are. So if you look, for example, New York is all here by itself, but the branch is very large, which means it's different than everything else. On the values that we looked at, it's different than everything else. But if we look at Northern and Madison, we look at, they're very similar. We look at Commonwealth and Wisconsin, they're very similar. Together, these two pairs are very similar, and they wind up on the same branch that doesn't have a lot of height. The dendrogram allows us to see, dependent on the height, we can see the similarity of the nodes that are at the end of it. So it's kind of significant in the way that it lays out. But it just shows us, kind of branches of where we might see different clusters. And it looks like we got one cluster here. New York's by itself. We got another cluster here. We got a fourth cluster here. And then this one seems to break out into two clusters. Central, Kentucky seem to break out by themselves. Florida is quite a bit different, but still clusters with Oklahoma, Texas, Arizona, and Southern. So our dendrogram tells us volumes of information just in the arrangement of the different utilities and the size of the branches and the positioning of the branches in the dendrogram. All right, that's hierarchical agglomerative clustering. And there's another kind of clustering we're going to go through today, and that's going to be k-means. Now, k-means is a different way of clustering. And what we're basically doing with k-means clustering is we are saying, all right, K, we're going to figure out what K is. K, we know this data set, a little bit about this data set, and we looked at it in the hierarchical clustering, and it looked a lot like there were 6 clusters. I think 6 is probably a good number. So what we're going to do is we're going to throw everything into a k-means clustering algorithm, and we're going to say there are 6 clusters, okay? And every one of the data points gets attached to one of the clusters. Then what we could do is we go through and we rearrange the clusters. We rearrange which of the 6 clusters each data point is connected to, such that when we look at the distance between the center of the cluster and the actual data point, or the data points that are attached to that cluster, we want to drive that number to the lowest possible number. And the way that we calculate that is we take the mean. What is the mean of all of the data points around the center of a cluster? If we're not quite optimized, if we're not quite to the lowest possible arrangement, then we change things up until we get to the lowest possible arrangement. So the idea is kind of conceptually sort of maybe a bit confusing, but if you look at it visually, if we were to plot these data values and look at it visually, we would see 6 logical clusters. Just like we look in the dendrogram, we see 6 logical clusters. You would see that in a plot as well. Again, the plot would show us the clusters. We could also conceptually sort of imagine there being a centroid there and imagine there being a calculation of the mean distance from the center of all of the data points in each cluster, and we want to drive that down. So what we do is we don't necessarily move the data points, but we might move the mean, and we might move which data points belong to which clusters. Okay, that's probably better explained in the book, so I'll let you read about it in the book. But we'll go through and sort of take a look at it. We're going to reload our data, reset our row names, get rid of the row name duplicate there. We'll go ahead and normalize the data, just like we did before, and set the row names into the normalization set. That's all good. And now we're going to run k-means. We'll set a value km, set equal to k-means, And what we're doing is we're running k-means on utilities.df.norm. That's our normalized data set. And we're telling it there are 6. K is 6. We are going to set up with 6 clusters. Okay. We can always change this. If 6 turns out not to be the right number, or if it just doesn't look right, we change it to 7, or we change it to 5. But from our data set, from what we saw in the dendrogram, it looked like 6 was a good number. So we'll stick with 6. Okay. And now we're going to show the cluster. And there it is, right? What this is these are all of the values that we had, and it shows us which cluster number they belong to. Okay, Arizona is in cluster 3, Boston is in cluster 2, Central is in cluster 3, Commonwealth cluster 4. You'll notice something that's kind of curious and kind of matches our dendrogram. New York is in cluster 1 all by itself. There are no other members of that cluster. That makes sense because remember the branch that we saw in the dendrogram. It was all by itself. But we do see relationships between Arizona, Florida, Kentucky, and Oklahoma. All of those fell into cluster number 3. And we saw relationships between Nevada and Idaho, and I believe there was Puget in here. It's got to be here somewhere. I don't see it. I don't know what. Oh, there it is. Puget. Okay. So those all fell into cluster 6. So it's basically giving us kind of something that looks really similar to what we had in the dendrogram, but this is information that we can dump out into a data frame and actually utilize or attach it to the data set that we have. And if you think about it also, our clustering values, what it did is it created KM. KM is basically it's a structure that holds everything that we need to know about that particular cluster. So KM allows us to see many different things about a cluster. A couple of other things that I want you to look at. We look at the centroids. Remember we calculated centroids for each of our values, and it gives us those. And then one last thing, we'll take a quick look at a summary command of KM, and you can see all of the stuff that it gives us when we run that k-means cluster. Now I've talked about k-means as being we're calculating using the mean distance. We could also, if we wanted to, calculate using the median. And if we calculate using the median distance, what that allows us to do is there's a great deal of variability in our data set, meaning that we might come up with 6 clusters, and those 6 clusters might be logical clusters, but there's just a whole lot of variability, just like what we saw with the New York data element in the dendrogram. If we had a lot of those, we might want to go ahead and go with median, because what it would do is it would control for outliers, where we saw the giant outliers that are throwing off our cluster. So that's another method we can use, and it's just another thing we can do in R. So what do I want you to do for this week? I've listed it out in the assignment. What I want you to do is run through this. I want you to download the file. I want you to download the script. And I want you to run through the script. I want you to generate the 2 dendrograms just to make sure that you can get those going. Then I want you to run the k-means cluster. Show me the table of different clusters where each of the different utilities winds up, whether it's cluster 1 through 6. Then give me the centroids and give me the summary KM results. Put that all into a Word document and upload that as this week's assignment. Let me know if you have any questions. Thanks.